Good afternoon, good morning, everyone. So I'm Michaël Marcozzi from Imperial College London, and I will present you this work, which is a joint work with Qiyi, who is just there, and also with Ali and Cristian. And I will start immediately by giving you the context of our work, which is actually compiler fuzzing. Actually, software developers rely quite intensively on compilers in their everyday work, and they do it often with some kind of a blind confidence. But in practice, compilers are nothing else than software, and like in any piece of software, there are bugs in compilers. For example, if you have a look at this graph here at the bottom of the slide, you can see this blue line, which shows that there are more or less 150 bugs that are fixed each month in the LLVM popular compiler. And in the worst case, actually, the consequence of a compiler bug is what we call an unnoticed miscompilation, which actually means that the compiler will silently generate wrong binary code that might then be executed at application runtime, making the application misbehave or crash, which can have really bad consequences for the society. And in order to avoid this, all the classical software validation approaches have been applied to compilers. So notably, there have been a lot of formal verification of compiler with this ComCert verified compiler, but also the alive prover that has been used to prove the correctness of peep-all optimizations in LLVM. And there have also been a lot, of course, of testing of compiler, like, for example, this LLVM test suite. And among all the testing techniques for compilers, there have been there have been a recent surge of interest in a specific technique called compiler fuzzing. So in a nutshell, the idea is to generate automatically and massively random test programs that are fed to the compiler. And then this is coupled with an automatic mechanism to detect if these programs fed to the compiler have been miscompiled. And this is done using some kind of either differential or metamorphic testing. And by using this compiler fuzzing approach, there have been notably more than 200 miscompilations that have been found in LLVM by the four state-of-the-art approach, which are CSMIS, Equivalence Modulo Input, EMI, Orange, and also IntelliAbgen. And actually, the problem that we actually want to solve in this work is that the importance of these miscompilation bugs found by fuzzer is unclear. So when we give talks on compiler fuzzers, quite often the audience will question the importance of the bugs that have been found by the fuzzer. And in our experience, this is a contentious debate where actually people can really be pulled apart. So for example, if you have a look at this greenish quote here on the slide. It's a quote from an anonymous reviewer of the paper at a top programming language conference, and the reviewer said, "In my opinion, compiler bugs are extremely dangerous, period. Techniques that can uncover and help fix compiler bugs are extremely valuable." And in the other end, you have this reddish quote here, which is from a guy who contacted us while we were working on this topic. So the guy is a former UK representative at the ISO International C Standard. And you can read on his blog that this sentence, so I would suggest that compiler developers stop responding to researchers working on fuzzers because responding just encourages the trolls. So yeah, given this, in our work, in this work, we have chosen to consider that we are working with a mature compiler in a non-critical environment. So as the compiler is mature, it has been intensively tested by both its developers and end users. And as we are in a non-critical environment, trade-offs between the reliability of software and the cost to develop software are actually quite acceptable and even common. And in such a context of a mature compiler in a non-critical environment, doubting the impact of fuzzer-found bugs is actually reasonable for at least two main reasons. First, it is unclear if mature compilers leave enough space to find severe bugs in them, because maybe all of these bugs have already been found by this intensive testing by developers and users. And secondly, fuzzers find bugs that will affect the code that they generate, and which is artificial code, so that these fuzzer-found bugs might affect patterns that only may appear in generated code, but may quite never appear in real code. And our goal in this work is actually to provide a study of the practical impact of miscompilation bugs. Do this like that. So more precisely, our objectives are not to show specifically that compiler fuzzing matters or does not matter, but first to study the impact of miscompilation bugs in a mature compiler over real applications, in order to check if there is indeed space and room in a mature compiler to find severe bugs, and secondly, to compare the impact of the bugs, depending on the fact that they were found by fuzzers while compiling artificially generated code, or by other means, like typically bugs found while real people were compiling their real code, in order to check if the bugs found by fuzzer with artificial code would have less impact than the other ones. And so to achieve these goals, actually, operationally, we had to overcome the two following challenges in this work. First, take steps toward a methodology to measure the impact of a miscompilation bug, and then apply this methodology over a significant but still tractable set of bugs and real applications. And in the rest of this presentation, I will first introduce our methodology, and then show you the experiments that we have done using this methodology and the results that we have obtained. So let's start with the methodology. So as a first assumption, we have chosen to restrict ourselves to publicly fixed bugs in open source compilers. And this enables us to extract the fixing patch for the bug that has been written by the compiler developers. And together with this fixing patch, we can get the source code of the compiler just before this fixing patch was applied, which we call the buggy compiler source code, and also the source code of the compiler just after this fixing patch was applied, which we call the fixed compiler source code. And as a second assumption, we have chosen to liken the impact of a miscompilation bug to the ability to its ability to change the semantics of real applications that would be compiled by a compiler affected by the bug. And given these two assumptions, we estimate the impact of the compiler bug over a real application in three stages. First, we check if the buggy code in the compiler is reached and the bug is triggered when the app is being compiled. If the bug is compiled during application compilation, then we check how much this triggering of the bug will change the binary code which is generated by the compiler for the application. And if there are such changes in the binary code, then we check if these changes can lead to differences in the runtime behavior of the binary when it is executed. And now I will give you much more details about each of these three steps. So let's start with step one, which is the compile time analysis. So on the left of the slide, you can see here actually the code section in the buggy compiler, which is affected by the bug. So actually what do we have? It's just an if statement. And if this condition is true, the compiler applies a code transformation to the code being compiled. And actually the bug was, this is actually a real bug. This is LLVM bug 26323. And actually, this bug was fixed in this way. So this is the same code section in the fixed compiler. And you can actually see that the compiler developers have kept the original condition here, but they've added an additional condition. And so what happened was that originally in the bug was that the condition was not strong enough, so that the code transformation was sometimes applied mistakenly, leading to the application being miscompiled. And by strengthening the condition here, the code transformation is now only applied when it's legal to do so. And what we do in actually in this first stage is that we craft a third version of the compiler, which actually is obtained by manually adding some warnings in the code of the fixed compiler. And we add warnings when the fixing patch is reached and the bug triggered. So this is how this warning laden compiler looks like with this bug. So actually we add a warning when we reach this code section that is affected by the fixing patch. And then for the triggering of the bug, actually the bug will be triggered if the code transformation is applied by the buggy compiler, but it is not by the fixed compiler. And this will happen if this condition is true, but the added condition here in the fixed compiler is false. And we check that the original condition is true, but the additional one is false. And if so, we print this warning saying that the bug is triggered. And when we have manually crafted this warning laden compiler, we take the source code of our application and we compile it with this warning laden compiler. And we obtain obviously a binary for the application together with compilation logs, which we grab for our two warning messages. And if these two messages are printed in the logs during compilation, it means that the fixing patch has been reached and the bug triggered when the app source code was compiled. And if the bug triggered, we switch to stage 2. We keep in stage 2 our buggy compiler and our fixed compiler. We take again the source code of our application and we compile it with both compiler, which will lead us to two binaries for the same source application, one produced by the buggy compiler and one produced by the fixed compiler. And then we disassembly these two binaries and we check for syntactic differences in this assembly and count if there are many of them. And if there are such syntactic differences, then we switch to stage 3, where we actually keep these two binaries. And we run the application test suite with each of the binaries. And what we do is that we check for tests which would fail when run with the binary that has been compiled by the buggy compiler, but which are okay with the binary compiled by the fixed compiler. And so what should be noted is that if we don't measure here any test divergence, it does not mean that the two binaries are semantically equivalent. It may just mean that the test suite was not strong enough to show that that a miscompilation happened. And so in order to alleviate this, what we did is that we took a sample of the differences at the assembly level that we code at stage 2. And we inspect them and try to manually craft inputs that would trigger runtime divergence because of this difference in the binary and assembly code. So yeah. So this was our the 3 stages of our methodology. And now let's have a look at our experiments and results. So our experiment is just actually to apply these 3 stages of the methodology over a sample of 45 miscompilation bugs from LLVM. And in those 45 bugs, there are 27 that are further found bugs, and this represents a sample of 12% of all the fixed miscompilation bugs found in LLVM by C-Smith, EMI, Orange, and Yabgen. And together with these 27 bugs, there are also 10 bugs that were detected by compiling real code with LLVM, and also 8 bugs that were found as the byproduct of applying the Alive formal verification tool over LLVM. And so our experiments are just to apply the 3 stages of our methodology to evaluate the impact of these 45 bugs over 309 Debian packages, totaling more than 10 million lines of code, which were selected so that they are not part of the LLVM test suite, and they represent a diverse set of applications with respect to their type, size, popularity, and maturity. And examples of such packages are Apache, Samba, and grep. And so after a lot of effort and 5 months of computation, we obtained the following results. So you have the fraction of package builds for which the patch is reached at stage 1, the bug triggered at stage 1. We get different binaries at stage 2 between the buggy and fixed compiler, and we spot a test divergence at stage 3. In blue, you have the result for the further found bugs. In green, for the bugs affecting real code, and in orange, the one for verification bugs. So you can see that at stage 1, for a significant fraction of package builds, the patch is reached and the bug triggered, with a slight advantage for the further found bugs. But at stage 2, you have only quite a small fraction of package builds for which you get different binaries. And actually, when you look at the assembly code, only actually a really teeny fraction of this assembly code is affected by the changes due to the fixing patch being applied to the fixed compiler. And in the end, for stage 3, we spotted one test failure in ZSH, in the ZSH package for the further found bug, and one extra failure in SQLite during additional experiments, and one test failure in the LevelDB package for the bugs affecting real code. And so we took a sample of our test suites, which have actually a 47, we measured the coverage, and they have a 47 average statement coverage. And for half of the test suites, they have more than 50% statement coverage. And we also made this manual inspection of about 50 binary differences, and this shows that they either have no semantic impact or that they require very specific runtime circumstances to impact the runtime behavior of the application. And so let's go to the conclusions. So our 2 major takeaways are that miscompilation bugs in a mature compiler impact quite infrequently the reliability of applications in the wild, at least as we have probed it with test suites and manual inspection. And they seem to have a similar impact, no matter the fact that they were found using real code or artificial further generated code. And a possible explainer for these results is that in a mature compiler, all the bugs that will affect patterns that are frequent in real code will have already been fixed because found by this intensive exercising of the compiler by developers and users, and so that there remain only corner case bugs that will affect real and generated code in a similar way. So actually a preprint and totally reusable artifact are available on this website. If you like this kind of research, we also have a postdoc position available in the group. And if you like the presentation, do not hesitate to have a look at my website and follow me on Twitter. I'm also on the job market. I'm looking for a position too. So thank you very much for listening to this talk, and it will be my pleasure to answer your question. Thank you very much. Okay, let's go.